Okay, this is the third of our drawing IV characteristics of devices video, but the device that we're looking at today is a much more complicated one. It's a diode. Now, diode is a piece of semiconductor, or it's a semiconductor device in the same way that the transistors that run your phone or your computer or this phone doing the videoing is a semiconductor device, and so doesn't have the same forward behaviour as backward behaviour. Sometimes we indicate it's a semiconductor by actually drawing a circle around it, but that's not strictly necessary. Because it has different forward to backward behaviour, the symbol itself has a directionality about it. You can see it's sort of an arrow pointing that way. So the symbol has some sort of directionality about it. Now, they're slightly tender because they're semiconductors. They're not chunky bits of metal that we can put a lot of current through. But these ones that we're lucky enough to have in Victoria College actually are pretty chunky, and they're actually attached to a piece of aluminium, so that if they get hot, they'll get the piece of aluminium hot. That'll radiate some of the heat away. Basically, the aluminium's acting as a heat sink, takes some of that heat away from the diode, so the diode will survive. So we've got nice chunky diodes that will survive a lot of current. I suspect a lot of schools find this very difficult practical to do, because they will have little tiny semiconductor diodes that burn out as soon as you put a big current through them. The only trouble with our diodes is that whoever installed them didn't necessarily get the red and black the right way round, which is rather irritating. Happened a very long time before my arrival here at Victoria College, and because you can see we'd have to unsolder it and things to put it back, to put them all the right way around, and we don't bother. So the red and black might end up confusing you, confusing me as we do this. Now, because it's quite tender, we've got a different circuit set up here. In order to see what's going on and the interesting bits of the characteristic for a diode, we have to use a potential divider, because a potential divider gives me a lot more control over what's going on than the output of one of my trusty power supplies. The power supply, you've seen in the earlier two videos, its output voltage is not what it says on the front. Its output voltage depends on what it's plugged into. That's not very helpful in this case. I want fine control on the output voltage, because all of the interest in the IV characteristic of a diode is right when it's just turning on. So I want to put my voltage up in really small steps. So that means we're going to be using a potential divider. Now, it looks like a great big long resistor. It is indeed a great big long resistor. This is a piece of resistive wire, and so it is all coiled around, make a resistor. So it is indeed a great long resistor. The difference is that it has a slider on the top, and that slider allows us to choose how much of that resistive coil the output sees. This is the output. This is that. That represents that. So we get to choose by how far we slide that along, how much of that coil the circuit is actually seeing. It's similar to the behaviour of a variable resistor. We could wire this thing as a variable resistor. It's called a rheostat. You can perhaps see that written on the top there. But today we're going to wire it as a potential divider, because a potential divider gives us much finer control of what's going on. Now, one of the sets has already had a go at having a look at what changing the slider does to changing the output of our potential divider. And the other sets haven't necessarily done that, so I'll just very quickly, you don't have to write these results down, that one doesn't feel like it's making good contact. Just choose a different one. So, the output of my power supply is going into either end of my resistor. Either end of my resistor. Now, we tie together the negative side of the circuit. Negative side of the circuit is often called common. the common side of the circuit. So this is the side of the circuit. If you're joining things together, you tie together the common side of the circuit. So I'm going to tie up the common side of the circuit. Now I'm going to put the diode in a bit, but I just want to show you what it is a potential divider does. So I'm going to put 6 volts on my power supply. If I remember to turn it on. And you see I've got an output voltage, and now I haven't got a diode in there. All I've got is I've got the voltmeter measuring what's coming out of my potential divider. And you can see I put 6 volts on. You can see I've got it about halfway. I've got about half 6 volts coming out of it. If I slide it up to the top, I get a lot more volts coming out of it. I'll slide it down to the bottom, I've got a lot less volts coming out of it. So a potential divider allows you to choose your output voltage depending upon how far up your slider is. Okay, useful little thing. And sometimes it's an exam question to understand a potential divider. Now I'm going to wire this properly with the diode in there. So move the voltmeter down here. I've put the ammeter in on the negative side. You remember me doing that in the last one. Doesn't matter. The ammeter needs to go anywhere in the loop that contains the diode. I'm going to put it in on the negative side. Most negative bit of the ammeter to the most negative bit of the circuit. The bit that's closest to the negative on the power supply. Also, of course, thinking about it as tying all the commons together. And I'm going to take the output of that, and I'm going to put the output of that into my diode. Now I suspect my diode's the wrong way around, the red and the black, so I'm going to start off that way and we'll see if I'm right, that the red and the black are wrong. And then that loops back round to there. There you go, that's that looped back round to there. And then, as always, voltmeter goes in last. Voltmeter goes in last across thing that we're interested in. So the thing we're interested in this time is the diode, so the voltmeter goes in last across the diode. There we go, more complicated circuit. So we've come out of the power supply, and the power supply is feeding my potential divider. It's going all the way across my potential divider. And then I'm going to use my potential divider to control the electricity going into my circuit rather than the power supply, or I might use a combination of both of them because I've got much finer control with the potential divider. Then in the loop that's actually doing something rather than just feeding us power, I've got an ammeter, I've got a diode. What did I just pull out? I'm going to put that connection to the ammeter. That connection might turn out to be a pain in the bum. Might have to swap that wire. And that then goes back to the potential divider, and I've got a voltmeter across showing me what's going on. Okay, let's have a look, see if we actually get something. Right, I've got a voltage and I've got a current. Now notice, now that I've put the diode in, even though I've got that slider quite a long way across, I've only got a tiny voltage. The output of the potential divider does change depending on what's on it, but I still do have quite fine control. So I've got a current and I've got a voltage. Now, what I need to do is I need to decide what steps we're going to conduct this experiment in. I'm just move it for you, it's about to fall off the desk. What steps are we going to conduct this experiment in? So what's the maximum I can get here? Let's slide it all the way up. 0.7, we can do better than that. Let's push the power supply up a bit. 0.8. What can I do? Can I get up to 0.9? Yeah, if I'm careful I can get up to 0.9. I doubt I can get any higher than that. Okay. So, I'm going to start at 0 and I'm going to go up in steps of roughly 0.1 of a volt. So that's going to give us 9 steps in the forward direction, and then we'll have a look at what happens in the reverse direction. I can't leave it there because you can see that's got 5 amps running through it. So that's right, doing that any good. That really will be getting hot, and even without us having heat sinks, that's going to be problematic. So let's have a go. So take me a little while because I've got to set this voltage now to 0.1. Ooh, hit it first time. Okay, so my volts are reading 0.1, my current is reading 0. My volts are reading 0.2. My current is reading 0. My volts are reading 0.3. My current is reading 0. My volts are reading 0.4. My current is reading 0. Oh, you see that? My current's gone up. My volts are reading 0.5. My current is reading 0.04 of an amp. Yeah, notice I've moved it a long way now. It's not behaving the same anymore. Now that I've got a current, all of a sudden I've got to slide it a long way. Clearly this is non-linear. Okay, my voltage is reading 0.60 and my current is reading 0.15. Okay, so my voltage is reading 0.70 and my current has shot up to nearly an amp. It's reading 0.94. An amp's a lot going around a circuit. An amp gets a circuit hot quickly. Let's push it up to 0.8. And my voltage is reading 0.80 and my current is reading 3.07 amps. Right, let's see if I can make 0.9. Yeah, there's 0.9. Missed it. My voltage is reading 0.9 and my current is reading 0.626. Properly scary amount. I'll just turn that off for a second so that it doesn't all burn out. Now, when you get a non-linear characteristic, and this is very clearly not a straight line, I hope you can all see that. When you get a non-linear characteristic, what you should do is you should go back and take more results where it's changing the most, so that you've got as much detail on the curve as you possibly can. So there's no point at all in me going back and putting in extra steps, running up to about 0.5 of a volt, because the current did nothing. But after 0.5 of a volt, the current shot up. And so I should, if I'm being a proper scientist, I should go back and put extra steps in after 0.5. Now, therefore, I'm going to go back and do a few more steps. It might mess up your table. You might have to pause this and do a different table. But I'm going to go back and I'm going to put in 0.55, 0.65, 0.75, 0.85 and have a look how that, just so that we've got some extra steps where the current is changing the most. 'Cause that's good science. Okay, so 0.55 gives us 0.08 on the ammeter. 0.6, let's just check it's consistent. Not quite at 0.6. Still not quite at 0.6, come on. 0.6 is giving us 0.16. 0.65 is the next stop, isn't it? 0.65, giving us 0.41. 0.70, just recheck it. Bit high. 0.70, 0.98 on the ammeter. And 0.75, not quite there. 0.75 is giving me 1.76 on the ammeter. So I'm going to try 0.8, 0.80, 2.90 on the ammeter. 0.85, just missed it. Really don't want to, I want to be doing this quickly because I'm going to burn out my diode. I don't like this much current going through them. Oh, I'm going to struggle here, aren't I? 0.84 I can get. Let's just try 0.8. Can I get 0.85? Oh, you swine, come on. Right, 0.85 is giving me 4.60. And I'll just try 0.9. Hard to hit exactly the same value as I hit the last time. So I'm a fraction high here, so I expect the current to be a fraction higher. 0.90 is giving me 6.38 amps. And my diode, yeah, that's hot. Ow. Ow. Okay, so a non-linear characteristic, and we've only done the forward direction so far. So we've got to have a look what happens when we reverse it. Now, previously, I've reversed the whole circuit. Sure, yeah, let's reverse the whole circuit. Okay. Let me just... Okay, I don't normally reverse the whole circuit on this one, but why not? Let's reverse the whole circuit. So current should now be flowing the other way. 0 gives me 0. Let's start pushing the voltage. Oh, did you see that shot up straight away? So minus 0.5, which we are on the forward direction, was starting to give us a current. Nothing. Minus 1 volt. Current. Nothing. Minus 2 volts. Current. Nothing. Minus 3 volts. Current. Nothing. Minus 4 volts. Surprise, surprise. Nothing. Minus 5 volts. Nothing that can be measured for our ammeter.